We'll cover how to clean and align data from different sources, manage missing values, and apply feature engineering techniques, such as creating lagged returns and categorizing stocks by size and age. This workflow will help transform raw financial data into a format that's ready for machine learning and statistical modeling. In this video, we'll walk through the process of preparing stock market data for analysis, focusing on how to handle large datasets efficiently using Python. Whether you're new to data science or looking to refine your approach, this tutorial will provide essential steps for preparing financial data for analysis. We'll be working with stock prices, company data, and other financial metrics to generate meaningful insights for further analysis. By the end of this video, you'll understand how to manipulate financial data, calculate monthly returns, and create features that will set the foundation for building predictive models. This snippet begins by enabling inline plotting for visualizations directly in notebooks. It then imports several libraries and modules that will be utilized throughout the data preparation and analysis phases. There's a focus on data manipulation and statistical modeling with libraries like Pandas for handling data frames and NumPy for numerical operations. Key visualization libraries include Matplotlib for basic plotting and Seaborn for enhanced, aesthetically pleasing statistical graphics. The Quandl library is imported, which is commonly used for retrieving financial and economic data from its API. In terms of machine learning, it loads models from Sklearn-like decision trees for both classification and regression, linear regression models, and logistic regression, which are essential for predictive modeling. Data splitting and evaluation utilities are also included, such as train_test_split for splitting datasets into training and testing sets, and cross_val_score for validating model performance. Model tuning is facilitated through Grid Search CV, which helps optimize hyperparameters. For performance metrics, several tools are imported to assess model predictions: the ROC-AUC score for evaluating classification models, mean squared error for regression accuracy, and precision recall curves for analyzing model performance. Handling missing data is made easy with the imputer from Sklearn.preprocessing, which allows you to fill in gaps in datasets effectively. Finally, statsmodels.api brings in additional statistical modeling capabilities, and SIPI provides interpolation functions, crucial for smooth data analysis on various dimensions. Overall, this setup indicates a comprehensive toolkit geared towards preparing, analyzing, and modeling data effectively across various dimensions. This snippet starts by telling Python to ignore any warnings that could pop up during execution. This can be useful when you want to keep the output clean, especially when you might encounter non-critical warnings that aren't relevant to the task at hand. The next line sets the plotting style for Matplotlib to ggplot, which is inspired by the R programming language's ggplot2 library. This style has a distinctive look with a gray background, white grid lines, and a specific color palette. Using plt.style.use, ggplot makes any plots you create more visually appealing and easier to read without needing to define colors and grid styles manually. Overall, this snippet is about streamlining output and improving visualization aesthetics before diving into data plotting tasks. The code snippet utilizes the Pandas library to interact with an HDF5 file, specifically assets.h5, which contains various datasets related to financial assets. The with PD HDF store/data/assets.h5 as store statement opens the HDF5 file in a context manager, ensuring that the file is properly closed after the operations are completed. The store.info method is called to print metadata about the contents of the HDF5 file, which includes the names of the datasets, their types, and their shapes. The output reveals several datasets within the HDF5 file, each represented as a data frame. For instance, the dataset/Quandl/wiki/prices has a shape of 15,389,314, 12, indicating it contains over 15 million rows and 12 columns, likely representing various attributes of stock prices over time. The dataset/us_equities/stocks has a shape of 6,834, 6, suggesting it includes information on 6,834 stocks with 6 attributes each. The shapes of these datasets provide insight into the volume of data available for analysis. Following the metadata output, the code extracts the adjusted closing prices from the /quandl/wiki/prices dataset using prices equals store, quandl/wiki/prices, .adj_close.unstack, ticker. This operation selects the adj_close column and reshapes the data by unstacking it based on the ticker index, which likely represents different stock symbols. The result is a data frame where each column corresponds to a different stock ticker, allowing for easier comparison of adjusted closing prices across multiple stocks. Additionally, the line stocks equals store, us_equities/stocks, retrieves the entire dataset of U.S. equities, which can be used for further analysis or merging with the price data. This structured approach to data extraction and manipulation is essential for preparing financial data for analysis, enabling users to work with large datasets efficiently and effectively. This snippet is focusing on aligning two data frames, prices and stocks, based on their shared stock ticker symbols or identifiers. First, shared is created by finding the intersection of the column names in prices and the index in stocks. This means that shared will contain only the tickers that are present in both data frames. Next, prices is filtered to include only the data from the years 2010 to 2018 for those shared tickers. The syntax prices.lock, 2010:2018, shared, effectively slices the data frame to get the relevant date range and only the columns that exist in shared. Then, stocks is also filtered. It's being limited to just those rows that correspond to the shared tickers and is only keeping 3 specific columns: market cap, IPOIR, and sector. This ensures you're focusing on the most relevant information for the stocks that you also have price data for. The result is 2 data frames that are aligned by the common tickers, one containing price data over the specified period and the other containing key stock characteristics. The code snippet stocks.info is a method from the pandas library in Python, used to provide a concise summary of a data frame named stocks. This method is particularly useful for understanding the structure and contents of the data frame, which is essential for data preparation and analysis. The output indicates that the data frame contains 2,412 entries, indexed from A to ZUMZ. It has 3 columns: market cap, IPOIR, and sector. The market cap column has 2,407 non-null entries of type float64, suggesting that it contains numerical data representing the market capitalization of various stocks. The presence of non-null entries indicates that there are only a few missing values in this column. The IPOIR column, which also holds float64 data, has 1,065 non-null entries, indicating a significant number of missing values, which may require attention during data cleaning. The sector column is of object type and contains 2,372 non-null entries, suggesting it categorizes stocks into different sectors, with some missing values as well. The output also specifies the data types of the columns, with 2 being float64 and 1 being an object type. This information is crucial for understanding how to handle the data during analysis, as different data types may require different processing techniques. Finally, the memory usage of the data frame is noted as 75.4 kilobytes, which provides insight into the resource requirements for handling this dataset. Overall, this summary helps in assessing the completeness and structure of the data, guiding further data preparation steps. The code snippet prices.info is a method call from the pandas library in Python, which is used to provide a concise summary of a data frame named prices. This method is particularly useful for understanding the structure and characteristics of the dataset at a glance. The output reveals several key details about the data frame. The first line indicates the class type of the object, confirming that prices is a pandas data frame. Following this, the output specifies that the data frame has 2,113 entries, which suggests that there are 2,113 rows of data. The date range for these entries spans from January 4, 2010, to March 27, 2018, indicating that the dataset likely contains time series data related to prices over this period. The output also mentions that there are 2,412 columns, labeled from A to ZUMZ. This suggests a wide array of features or variables included in the dataset, which could represent different attributes related to the prices being analyzed. The mention of types, float 64, 2412, indicates that all columns are of the float 64 data type, meaning they contain numerical values, which is typical for price data. Lastly, the memory usage of the data frame is reported as 38.9 megabytes, providing insight into the amount of memory the dataset occupies in the system. This information can be useful for performance considerations, especially when working with large datasets. Overall, the prices.info method serves as a quick diagnostic tool to understand the basic structure and resource requirements of the data frame, which is essential for effective data preparation and analysis. This snippet processes financial price data to calculate monthly returns. It begins with the prices data frame, which is likely made up of time series price data. First, the code resamples the data to a monthly frequency using .resample, m. The .last method is called to grab the last price of each month, which is essential for calculating returns between months. Then, the .pct_change function calculates the percentage change from one month to the next, giving us the monthly returns. Next, the code uses .stack to transform the data frame from a wide format to a long format, making it easier to manage. The .swap level then rearranges the multi-level index if needed, generally to make the data easier to work with in subsequent steps. The results are filtered using returns.between, which isolates values that fall between the 5th and 95th quantiles, effectively trimming outliers from both ends of the distribution. After filtering, the resulting series is converted into a data frame with a column named returns using .to_frame, returns. In summary, this code sequence transforms monthly price data into a clean summary of returns, excludes extreme values, and prepares it for further analysis. This snippet is focusing on creating lagged return features from a data frame called returns. The loop goes through a range of numbers from 1 to 12, where each number represents a lag or a time step moving back in time. For each t, the code generates a new column in the returns data frame, named according to the current lag, like T1, T2, etc. Inside the loop, it uses group B on the data frame based on the ticker level, meaning that it's handling data separately for each stock or asset represented by the ticker. The shift, T, function then shifts the returns for each ticker down by T periods, essentially creating a lagged version of the returns. After all the lagged features are created, it calls dropna, to remove any rows that contain NaN values. This is important because when we shift the data, the first few rows for each ticker will have null values since there isn't enough historical data to generate a lagged return for those periods. So by the end of this block, you'll have a data frame that includes the original returns along with new columns showing what the returns were in the previous 1 to 12 time periods for each ticker, while also ensuring there are no missing values. This snippet of code is manipulating a data frame called returns, which likely has a multi-level index including a level for dates. First, it's resetting the index for date. This is useful if we want to ensure that date is treated like a regular column instead of being part of the index. Next, it retrieves the date level of the index and extracts the year and month components from it. The line dates equals returns.index.get_level_values, date, gathers all the date values from the index, and then returns, year equals dates.year and returns, month equals dates.month create new columns in the data frame for the year and month. Finally, it uses pd_get_dummies, to create dummy/indicator variables for both the year and month columns. This is a common technique in data prep for machine learning to convert categorical variables into a numerical format that models can process effectively. Each unique year and month will have its own column, filled with zeros and ones indicating the presence of that year or month in the original data. This makes the data frame much more suitable for later analysis or modeling. The code snippet returns.info is a method call from the pandas library in Python, which provides a concise summary of a data frame named returns. This data frame contains a total of 171,162 entries, indicating a substantial dataset that spans from February 28, 2011, to March 31, 2018. The output reveals that the data frame has a multi-index structure, which is useful for organizing data across multiple dimensions, such as time periods or categories. The summary includes details about the columns in the data frame, totaling 33. The first column, labeled returns, consists of floating point numbers, float 64, and contains no null values, suggesting that all entries are valid and complete. The subsequent columns represent various time-related features, including years from 2011 to 2018 and months from 1 to 12, all of which are stored as unsigned integers, uint8. The absence of null values in these columns indicates that the dataset is fully populated for the specified time range. Additionally, the memory usage of the data frame is reported as approximately 20.7 megabytes, which provides insight into the resource requirements for handling this dataset. This information is crucial for understanding the efficiency of data processing and manipulation tasks that may be performed on the data frame. Overall, the output from returns.info serves as a foundational overview, allowing users to grasp the structure and completeness of the dataset before proceeding with further analysis or modeling. This snippet is creating a new column called age in the stocks data frame, based on the IPOIR column. First, it's using pd_cut to categorize the IPOIR data into quantiles. The q equals 5 argument specifies that it will divide the data into 5 equal parts. The labels equals list, range, 1, 6, assigns numbers 1 through 5 to each quantile, which effectively ranks the IPO years into 5 groups. The resulting series from pd_cut is then converted to floats with datatype, float. After that, any missing values are filled with zeros using .fillna, 0, and finally, it converts everything back to integers with datatype, int. After creating the age column, the original IPOIR column is dropped from the data frame with stocks.drop, IPOIR, axis equals 1, cleaning up the data frame by removing this now redundant data. The code snippet stocks.info is a method from the pandas library in Python, which is used to provide a concise summary of a data frame. In this case, the data frame appears to contain stock-related data, and the output reveals several key characteristics of the dataset. The output indicates that the data frame consists of 2,412 entries, which suggests that there are 2,412 rows of data. The index ranges from A to ZUMZ, indicating that the entries are likely labeled with stock symbols or identifiers. There are 3 columns in the data frame: market cap, sector, and age. Each column has a specific number of non-null entries, which is crucial for understanding the completeness of the data. For instance, the market cap column has 2,407 non-null float 64 values, meaning that 5 entries are missing data in this column. The sector column has 2,372 non-null object entries, indicating that there are 40 missing values in this categorical data. The age column, on the other hand, contains 2,412 non-null int 64 values, suggesting that this column is complete with no missing data. The data types of the columns are also specified, with market cap being a float 64 type, age as int 64, and sector as an object type, which typically represents strings in pandas. This information is essential for understanding how to manipulate and analyze the data effectively. Lastly, the memory usage of the data frame is reported as approximately 155.4 kilobytes, which provides insight into the resource requirements for handling this dataset. Overall, the stocks.info method serves as a valuable tool for quickly assessing the structure and quality of the data, allowing users to identify any potential issues, such as missing values, and to understand the types of data they are working with. This foundational understanding is crucial for any subsequent data preparation and analysis tasks. The code snippet stocks.marketcap.head is used to retrieve the first few entries from a data frame column named market cap, which likely contains the market capitalization values of various stocks. This function is part of the pandas library in Python, which is commonly used for data manipulation and analysis. The head method, by default, returns the first 5 rows of the specified data frame, allowing users to quickly inspect the data without displaying the entire dataset. The output shows a list of stock tickers along with their corresponding market capitalization values in scientific notation. For instance, the ticker A has a market cap of approximately 19.6 billion, while AA has about 8.54 billion. The values are represented as floating point numbers, indicated by the type float 64, which is a common data type for numerical values in pandas. This format allows for a wide range of values, accommodating both very large and very small numbers. The market capitalization values provide insight into the size and value of the companies represented by the tickers. A higher market cap typically indicates a larger, more established company, while a lower market cap may suggest a smaller or less established entity. This information is crucial for investors and analysts when evaluating potential investments or understanding market dynamics. Overall, this code snippet and its output serve as a foundational step in preparing and analyzing financial data related to stock performance. This snippet is about categorizing stocks based on their market capitalization. It uses the PD_cut function from the pandas library to divide the market cap column into 10 quantiles. Each quantile is assigned a label from 1 to 10, which will give a ranking to each stock according to its market cap size. The result is stored in a new column called size. This means that stocks with smaller market caps will have lower values in size, whereas larger market caps will have higher values. After categorizing the data, the code then removes the original market cap column from the data frame, keeping only the new size column along with any other existing data. This is done using the drop method, specifying to remove the column with axis equals 1. So now, you have a more streamlined data frame that focuses on the size categorization rather than the raw market cap figures. The code snippet stocks.info is a method from the pandas library in Python, which is used to provide a concise summary of a data frame. This method is particularly useful for understanding the structure and contents of the data frame, which in this case appears to be related to stock data. The output indicates that the data frame contains 2,412 entries, indexed from A to ZUMZ. It has a total of 3 columns: sector, age, and size. The sector column has 2,372 non-null entries, suggesting that there are some missing values in this column. The age column is fully populated with 2,412 non-null entries, indicating that every entry has a corresponding age value. The size column has 2,407 non-null entries, which also points to a few missing values. In terms of data types, the output shows that sector is categorized as an object type, which typically means it contains string data. The age column is of type int64, indicating it contains integer values, while the size column is categorized as a category type, which is often used for categorical data that can take on a limited, fixed number of possible values. The memory usage of the data frame is approximately 139.3 kilobytes, which provides insight into the amount of memory the data frame occupies in memory. Overall, this summary gives a clear picture of the data frame structure, including the number of entries, the presence of missing values, the data types of each column, and the memory footprint, all of which are essential for data analysis and preparation tasks. The code snippet utilizes the PD_get_dummies function from the pandas library to perform one-hot encoding on specific categorical columns of a data frame named stocks. This process transforms categorical variables into a format that can be provided to machine learning algorithms to improve predictions. In this case, the columns being transformed are size, age, and sector. The prefix and prefix underscore set parameters are used to customize the names of the new columns created from the categorical variables. For instance, the size and age columns will have their values prefixed with size underscore and age underscore, respectively, while the sector column will not have a prefix but will still be transformed into multiple binary columns. The output of the stocks.info method provides a summary of the data frame after the transformation. It indicates that the data frame now contains 2,412 entries and a total of 28 columns. Each of the new columns created from the one-hot encoding process is listed, showing that there are multiple binary columns for size, size underscore 1 to size underscore 10, and age, age underscore 0 to age underscore 5. Each of these columns contains 2,412 non-null entries, confirming that there are no missing values in the dataset. The original sector column has been transformed into several binary columns representing different sectors, which are also included in the output. The data types of the columns are specified as uint8, indicating that they are stored as unsigned 8-bit integers, which is efficient for memory usage. The total memory usage of the data frame is approximately 164.8 kilobytes, reflecting the compact nature of the data after encoding. This transformation is crucial for preparing the data for further analysis or modeling, as it allows algorithms to interpret categorical data effectively. The code snippet processes a data frame named returns by performing several operations to prepare the data for analysis. Initially, it resets the index of returns based on the date column, which allows for easier merging with another data frame called stocks. The merging is done using the indices of both data frames, ensuring that the data aligns correctly based on the date. After merging, any rows with missing values are dropped, which is crucial for maintaining data integrity in subsequent analyses. The final step in this chain sets the date index as an additional index level, which can be useful for time series analysis. Following the data preparation, the code calculates the number of columns in the returns data frame and assigns this value to the variable s. It then modifies the data frame data by converting all columns beyond the s index to integers. This conversion is done using the astype int method, followed by apply pd to underscore numeric downcast equals integer, which optimizes memory usage by downcasting the integer types. This step is particularly important when dealing with large datasets, as it can significantly reduce memory consumption. The output of the code provides a summary of the resulting data frame, which has a multi-index structure with 171,162 entries spanning from March 31, 2011, to February 28, 2018. The data frame contains 61 columns, with a mix of float 64 and int8 data types. The presence of non-null entries across all columns indicates that the data is clean and ready for analysis. The columns include various time series data points, T1 to T12, year and month indicators, as well as demographic and industry-related features. The memory usage of the data frame is reported as 25.3 megabytes, reflecting the efficiency achieved through the data type conversions. Overall, this code effectively prepares the dataset for further analysis by ensuring it is clean, well-structured, and optimized for performance. This snippet is using the pandas library to save a dataset to an HDF5 file format, which is particularly efficient for storing large datasets. The pd-hdfstore function opens, or creates, an HDF5 file named data.h5. The context manager ensures that the file is properly closed after the operations are done, even if an error occurs. Inside the with block, the store.put method is called to store a variable named data in the HDF5 file under the key data. This puts the entire dataset into the file, allowing you to easily retrieve it later. The HDF5 format is great because it supports complex data structures and allows efficient reading and writing operations, which is particularly useful if you're working with large amounts of data. Overall, this approach is succinct and leverages the capabilities of pandas for efficient data storage.